Last time. I think we got all the way through. Right. Okay, so if F is in the Schwartz space, Adelic Schwartz space, try to remind you what that is. I think we've seen it enough times now. We proved the Poisson summation formula, Adelic Poisson summation formula, that when you sum F on the rationals, or you sum F hat on also the rationals, you get the same thing. And that continues to be the case when you, for any edelic, I guess I call this sometimes the dilated Poisson summation formula. When I dilate F by T, F hat dilates by 1 over T with a factor of 1 over the Adelic norm of T out front. That we proved this. From this, we made a theta function, theta F of T, which was all but the 0 term, which is a sum over Q in Q cross F of QT. Now, this is a function. Here's one of the places where we saw the difference between, just remind this, I'll review. The difference between what happens over the integers is that this is a multiplicative group, and we're doing a multiplicative translation. And so this is on the group, the edels mod Q. So T is in the edels, but this sum makes it invariant under Q. Should I already give a little bit of foreshadowing? The edels are GL1 of the adels. And it's just a trivial thing. And the multiplicative, the invertible rationals are GL1 of the rationals. So this is true, and it's a little bit of foreshadowing. We're going to change 1 to different things and then figure out, we won't be able to just write these down quite so easily, but the objects that we'll be interested in will be irreducible subspaces of the action of GL and A, or G of the adels more generally, on quotients like this, or square integral functions of quotients. So we have to make sense of all those things. That's what we're building up to. Anyway, the purpose of doing that, or the purpose of talking about this, is to motivate that. Why would we care about such things? So we had this theta function, and we took the, what's that?
Yeah, I suppose coming to class.
Oh, yeah. The motivation is, or one of the motivations, I mean, it's just kind of fun, but of course we want something out of this. What we get out of this is by taking the Adelic Mellin transform. This is all review. We took the Adelic Mellin transform. S is a complex number with, at least at first, the real part of S greater than 1, which is now an integral over this quotient of the theta function times this multiplicative character T to the S with multiplicative Haar measure D star T. We unfolded this. We unfolded this, and everything fell away, and it looked like we had nothing left. It was just F of T, T to the S, D cross T. But then we remembered that what it means to be Schwartz is that, so this factors as a product over all primes, including infinity, the local integrals QP cross F, FP, TP, the P norm D cross TP. But almost all of these FPs are just the indicator function of ZP, ZP cross. These are, well, they're all the indicator function of ZP, but then we're going to intersect it with QP cross. So actually, we're going to get everything but 0 in this integral. We did this integral already for those. So I want to just sit on this for a second. So if we take it's up to us to choose the test function. We could choose F to be f of t, or f of x. This is an Adelic. This is a number. This is an Adelic number. When we're summing, we're only summing over edels. But f initially is just a function on the adels, and in fact, that'll be important that it has a value at 0 and it has a Fourier transform, which we defined only on adels. So so we could choose f to be at the infinite place, e to the minus pi x infinity squared times, so f factors, times a product over all primes, the indicator function of zp of xp. That is a perfectly fine function. In fact, this is a nice function in our Schwartz space, in our Adelic Schwartz space. Almost all, in fact, in this case, all the finite places, we just get the indicator function. And here we get this exponential function. And so these two things are the same. So the indicator function of ZP is the p-adic Gaussian. And when we compute these integrals, then these integrals, shall I call them I of p or something? I of p is
transforms itself.
It is true that it's transform as itself. You'll see more of the analogy. It's not really a property of the Gaussian. It's the analogy that when we make this choice at that place, we get the p factor of the zeta function, which again, there's no reason to use the Gaussian to get the Fourier, to get the functional equation analytic continuation of zeta, but it's the classical thing to do, and actually there are good reasons for using it. But it's somewhat arbitrary, so it's not like I have a rigorous definition for what it means to be a Gaussian, and axiomatically the indicator function of ZP satisfies that. It's an analogy. Then these local integrals so I infinity, we computed this already. If this is the Gaussian, and you're integrating with the absolute value of t to the s, the x infinity over x infinity, we computed that integral, and we get something like 2 or a half times times pi to the minus s over 2 gamma of s over 2. This is the gamma function. And IP we also computed. In other words, all these other integrals we computed, and we got 1 over 1 minus 1 over p to the s. I'm just reminding you what we got last time. Now, the fact that for a typical f, it's not true that every single place is the indicator function of ZP, and the infinity place could be whatever it wants. So there's some finite product, which we have no control over, but eventually it looks like this, which means eventually these integrals look like this. And that infinite product comes out to almost the zeta function. With this choice, we literally get that the Mellin transform of the theta function at s is a complex variable. Again, this integral only converges if the real part of s is greater than 1, is literally the completed zeta function, pi to the minus s over 2, gamma s over 2, zeta of s. Or I should write this better as a product over all primes, 1 minus 1 over p to the s inverse, which of course is the zeta function. Or maybe not, of course. I keep forgetting what I'm allowed to assume and what I'm not. Do we know that this is the Euler product of the zeta function? Should we talk about why that's true classically? What this has to do with the other version of the zeta function that we had seen, which was 1 over n to the s? Should we talk about that? Teddy, do you know why that's true? Okay. Since Teddy knows, we're going to move on. Teddy's my benchmark. Unique factorization. Yes, exactly. Unique factorization. This is an exercise in unique factorization and what the Taylor series of the series expansion of 1 over 1 minus lambda being 1 plus lambda squared. So those two things together give you this idea. Okay. That is good. We found the zeta function, but we haven't learned anything new about it because this was all assuming the real part of S is greater than 1. And now we're going to go into what does the analytic continuation look like adelically. Does that make sense? So far, so good. So back to the general case, back to general F in the Schwartz space, for which this calculation is nearly the same, except I don't know exactly what the infinite place is, and finitely many places will have whatever integrals it has. It's up to us to choose whatever locally constant, compactly supported function we want. So we're back to the general case. Let's remember what this integral was. It was an integral over this quotient, a star mod q star, of the theta function of t to the s d star t. Now, before we unfold, let's remember what this, let me remind you how we did the unfolding. It was to recognize that we have a fundamental domain here. So recall this fixed fundamental domain. I guess I was calling it d star for lack of better notation. Remember what the fundamental domain for a cross mod q cross is? Other than Nick? Kirill, you want to tell us?
So 0, 1, multiplied.
Yeah, it's a product of ZPs. It would be ZPs, but we're in the edels. So ZP crosses. And 0, 1 would be for the adels modulo Q. The edels modulo Q cross. It's not translation, it's multiplication. Exactly. Okay, we remember this, right? We can take any, this was the strong approximation in the edels. Okay, what did we do classically? We broke the integral as an integral from 0 to 1 and 1 to infinity. What we're going to do adelically is very similar. So this is an integral. Now I can no longer, once I start messing with this, you see, each of these, the reason I can write a cross mod q cross is that this is a function that's invariant under q cross. This is a function, a norm, that's invariant under q cross. It's trivial on q. And this is the multiplicative Haar measure, which is invariant under multiplication by q cross. So there's no problem writing this. Once I start messing with things that aren't invariant under q cross, I'd better use a fixed fundamental domain. So let me say t in d cross. So that's my fixed domain. Everything else is the same. But I'm going to break this according to whether the adelic norm of t is bigger than 1 or less than 1. Less than or equal to, it doesn't matter because, as you'll see in a second, everything is the same. What does this actually mean?
Multiply together the things and check if they're bigger than 1 or not.
That's right.
That's not what.
I do. That's exactly what I mean. But given the t is in d cross, do you have a question, or you want to give the answer?
I have a question.
Oh, please.
Well, you're allowing it to equal 1 on both. There's some overlap.
I am allowing it to equal 1 on both, and you'll see in a second why that's okay. Yes. I don't want to do, I mean, it doesn't really matter, but you'll see in a second why it's okay to allow both. It's not obvious immediately that it's okay to allow both.
I was just thinking of the same way as like 0 to 1 and then 1 to infinity. 1 is included in both.
That's right.
I hope there's a measure 0 thing.
There's exactly a measure 0 thing going, but we have to get to the bottom of it.
Careful. The norm 1 things in CP are not measure 0.
Right.
CP cross is not measure 0.
Yeah, but there's like a lot, it's a lot stricter.
Well,
Plausible.
so let's figure this out. What's going on here?
Equals for both, then I'm trusting he's doing it.
No, you shouldn't trust me. No, never trust.
Circle's supposed to do this. Yeah.
That's right. That's right. So what is going on here? As Joy just said, this is the product over all the places of TPP. So how do we make sense of this? I mean, this could be anything, right? We could have some large places, some small values, large values. Could we?
It's less than one beyond some.
That's true. Beyond some point, the valuation is at most one. In fact, we're in D cross. So it's equal to one. And in fact, we're in D cross. So that point is the prime two. They're all in ZP cross. So they all have absolute value one. The only one that actually has a chance of not having absolute value one is T infinity. So this whole thing about the Adelic norm being greater than or less than one is just a question about T infinity. All the other norms are one on the nose. So that's why it's a measure zero phenomenon to put an equal sign or not equal sign. There is no p-adic question. Okay, does that make sense? All right, what's going on? Let's have a look at this first bit. So, well, let me isolate it. So I have this integral over T in D cross, Adelic absolute value, which is also equal to the infinity absolute value greater than one of what is this theta function? Let's recall it's a sum over Q in Q cross F of QT. Then I have a T to the S, Adelic norm, but of course, again, we're in D cross. So the only thing that gets a norm here, all the norms are one except the infinite norm, dt cross plus this other integral. So let's call this I less than or equal to. I just want to deal with this one for a second. What can we say about this function? If anything. This sum over Q and Q cross, recall, is nothing but a sum over the integers of f of n over some fixed capital N times t. Right? All of these sums, the sum over Q, we're going to take out the point. In fact, let's take out the point 0 right now, because that'll be crucial to making sense of this integral. But you remember that this sum over Q looks very strange, but the fact that f is a Schwartz function means that the denominator, for two different reasons, the denominator, the only Q's that arise on which f is non-zero, have a fixed denominator. So actually, this is a sum over the integers with a fixed denominator. That's the only rationals that will occur in this sum. And I've taken out the term Q equals 0, which corresponds to the term n equals 0 on this side. So it's a sum over non-zero integers here of a function which is Schwartz at the infinite place, and t is at least 1, or negative, less than -1 or greater than 1. And so this is actually this sum, this series, when integrated, is an entire function of S, exactly the same as before. You guys see that? Does that make sense? So the point is, we have this f infinity. Every other, at the other places, we're compactly supported and locally constant. Well, the fact that we're compactly supported means that we're bounded. Almost all of them are bounded by 1. And so the finite places just give us a constant. And then there's only the Schwartz function that we have in infinity. And the Schwartz function that we have in infinity means that as a function of t, with t being bigger than 1, this integral, this sum starting at 1 over n, capital N is fixed, determined by f. So this thing has no problem being summed and then integrated. Okay, so this first bit is an entire function of S. Does that make sense? For exactly the same reason as before. Did I lose you? Teddy, did I lose you? A little bit, be honest. Okay. Remember what happened before? Well, maybe I lost you before. Classically, we got to a sum over f n at least 1 n times t. And then we were integrating this, and we broke the integral from 0 to infinity into an integral from 1 to infinity with a t to the s dt over t. that ring a bell? And so the question was, well, this function f is Schwartz. So it's decaying faster than your favorite polynomial out at infinity. And so if I put absolute values here, the only thing that I see here is the real part of s. I'm not worried about an integral at 0. I'm only worried about an integral at infinity. At infinity, this is growing like some polynomial, but this is decaying faster than any polynomial. So no matter what the real part of s is, could be negative, could be, this will always still converge. And convergent, when you have absolutely convergent sums and integrals of holomorphic functions, the resulting thing is holomorphic. And so that's how you get something to be entire. You need uniform convergence on compacted, which we have in this case, because it doesn't matter what this real part is. You just take a little compact ball about it, uniform convergence. Does that make more sense now? So all I'm saying is, even though we're writing a sum over q and q cross, remember that's just a sum over the integers with an extra parameter, but that extra parameter does nothing to change the integrability of this. Now, at least I got Teddy. Anybody else feel better about this, the argument that this is entire? It would be, I mean, if you were to do this formally, like in Lean or something, there would be an awful lot of things you would have to check to make this right. I'm relying on your human intuition in some sense. Anyway, how would you do this? A topic for another time. It would be a pain. It would be a pain right now. All right. Shall we deal with what you do for the t's that are less than 1? Less than or equal to 1, since it doesn't matter. So far, so good. Any complaints about this entirety? In its entirety? Okay, let's go to what about the integral less than? The less than integral is the same integral. I'm just writing this again. Theta f of t to the s, multiplicative Haar measure. T is in this fundamental domain for the edels modulo the multiplicative rationals, invertible rationals, but now with norm less than 1. What we're going to do here is, remember, we have Poisson summation that says that theta, the theta function, where do I have this? The theta function is a sum over, all right, let me grab this. Grab this, copy, and paste. So here's Poisson summation again. If I take out the term at f equals 0, there's a term at f equals 0, so I'll move it to the other side. So minus f of 0. And let me take out the term r equals 0 here. And what I should add back in is the term at r equals 0, which is f hat of 0. And this is the theta function. This is theta f of t. This, well, without the 1 over t. Okay, let's keep the 1 over t. It's 1 over Adelic absolute value of t, theta of f hat, not at t, but at 1 over t. 1 over t, t is an edel, so it's invertible. So it makes sense to say 1 over. I hope this looks identical to the classical setting. This part of the argument is identical to the classical setting. So this integral we can write as integral over d cross t having absolute value less than 1. I'll replace the theta function by 1 over t, theta function of the Fourier transform at 1 over t. Let me already break it here. T to the s, d cross t, and then I have these contributions. So this is a plus an integral, Adelic integral over d cross t less than 1, f hat of 0, which is just a constant, over absolute value of t times t to the s, d cross t, and then one last term, which is f of 0. I guess this is a minus sign, f of 0, t to the s, d cross t over t less than 1. Okay, who's lost? Or can I show where? Yeah, okay. Hopefully you can see that. Can you see that? I haven't done the transformation yet.
Oh,
I'm about to do the transformation here. Here, we're just going to evaluate the integrals exactly. So far, so good. Okay. Good. Very good. So, what should we evaluate? Let's evaluate these guys, these pieces. Okay, let's evaluate these pieces. Okay, what are we going to do with this? This is the easy thing. We're going to make a change of variables. T goes to 1 over t. That's a group action. Inversion is a multiplicative group action. We can check that that does nothing to this. It changes from t being less than 1 to t being greater than 1. Maybe that's the easiest thing to do first. We're going to send t to 1 over t. This becomes an integral over t in this fundamental domain, but now with norm greater than 1, I have a theta function at f hat of t. I have an absolute value of t, which now becomes that to the minus 1. There was an extra factor of t here, so this is absolute value of t to the 1 minus s, and we're invariant under this map. Or we change by minus sign, but this also changes by minus sign. And so that bit, this bit is equal to that bit. And that bit looks an awful lot like the positive integral that we had. So that's again an entire function of s. And this is entire for s in the complex book. Okay, we just have to compute these integrals. So far, so good. Okay, f hat of 0 is a constant. F hat of 0 is a constant. I have a product here. This is not an integral over all of this is not an integral over all of the Adels like we had before. This is an integral just over this fundamental domain. So let's break it up. It's an integral in R. The integral in R goes from minus 1 to 1, I guess. And then I have a t infinity. So there's a t infinity, I guess in absolute value, raised to the s minus 1 power. And then d star is very good. Thank you. D is only positive. This condition at infinity is minus 1 to 1, but d is only the positive. So it really is just an integral from 0 to infinity. Thank you very much. T infinity to the s minus 1. This was just a constant that pulled out. D infinity t here is dt infinity over absolute value of t infinity, although you don't need the absolute value because everything's positive. Same thing here. You don't actually need this absolute value. And then what's going on at the finite places? What's going on at the finite places? So the fact that t has absolute value less than 1 doesn't contribute, because we're already we're just integrating over zp cross. So we get a product over p, an integral over zp cross. That's exactly what d star is. But what is absolute value of t, tp to the s, d star t? What's the absolute value of t on zp cross? You can say it, Joe. Is one. So this is just 1. This integral, by the normalization of the multiplicative p-adic par measure, it was normalized, so its integral over zp cross would be 1, and the product over all primes is 1. F hat of 0 is just a constant. Yep.
From my angle, your head is blocked.
I'm sorry.
Okay.
I'm used to writing on a board and then stepping away so people can see what I write. But I guess here I step the cursor away so you can see what but I need to move my head too. Yeah. So all of these, the point is, it looks like we're about to get some kind of zeta function or something here, but there's a very, very subtle difference between zp take away 0 and zp cross. It's exactly here where we feel that distinction. Because we're in d star. D star is zp cross. This goes back to our discussion about the different topologies on the edels, that it's not the subspace topology. Yes.
When we did our t goes to 1/t,
Yes.
we've got the minus sign out front, but why did?
Well, so it reverses the infinite place is infinity to 1 integral. And that minus sign changes this sign as well.
So that's, okay, so we get a minus sign from the harm measure.
We get a minus sign from the Haar measure. We get a minus sign from flipping infinity to 1 to 1 to infinity. Yeah. Which is exactly what happened classically as well. Okay, so the point is all of these products are 1. This integral, even I can evaluate this, it's t to the s minus 2 integrated from 0 to 1. So that's just 1 over s minus 1. F of 0 over s minus 1. That's this first term, not both terms, just the first term. And the other term, gosh, this is, I'll use underline 2. Underline 2 is for the second term. I don't think you need me to do this calculation very far. It's going to come out to the same f hat of 0. The product over the places, finite places, is going to be 1. And this thing is just integral t to the s. So I get a over s. Okay, so let's summarize. Summarize. Did I lose everybody? No, this makes sense. We're doing this calculation a second time. I guess I could have done it more slowly the first time, but the first time it was classical. So I'm doing the Adelic one slowly, even though anyway, whatever. Okay, so we started with this theta. We took its Mellin transform. When the real part of s was greater than 1, we found that it was equal to some integrals, some product over p in s of something, which is just a finite product, times zeta, times a product over primes not in s of the Euler factors of zeta. That was one calculation. A second calculation, when we didn't unfold, this was by unfolding. When we don't unfold and we leave the integral over this d star, we get two contributions. One contribution is an integral over t in d star of absolute value of t greater than or equal to 1. The theta function multiplied by t to the s with the multiplicative Haar measure. And there's a second very similar contribution from from one piece of the t less than 1 integral, which is theta of f hat of t of s of t, same t to the 1 minus s. And finally, we have two more terms, plus f hat of 0 over 1 minus s, which I'll write as minus f hat of 0 over 1 minus s, and a minus f of 0 of s. So in this sense, it's exactly the same thing as the concept, with a few things to check along the way. And so this gives, again, this thing is entire, this is entire. And so this has poles at s equals 0 and 1. And so there's our meromorphic continuation, meromorphic continuation of zeta, which is here, to all s. Okay, we didn't get anything all that new out of this. We got some new insights into, I mean, it's a kind of a cool, I think, I like this calculation that it comes out not to a series of zeta, but the Euler product. But what more can we get out of this? By the way, I guess I should say, what's the purpose of getting meromorphic continuation of zeta? What are the kinds of applications can we get out of this? I'm not going to prove the types of applications. You do get that. You get all kinds of things. I'm thinking more like the prime number theorem, right? So the prime number theorem, not the means, right? The physics means, prime number theorem. which is that the number of primes up to x is how does the prime counting function grow? You guys, other than the people who know. If you don't know, what do you think it is? Terrible question. You know what it is? Something about a law. Something about a law. Yeah. That's one way of putting it. Yeah. So this was Gauss's conjecture. It used to be called Gauss's conjecture. And Gauss said that the probability.
Why have we named it away from being named after Gauss?
Gauss has a lot of things named after him. That's true. That's true. Well, in some sense, right. The prime number theorem. Well, Riemann explained how you should use this fact. Okay, so this fact, I guess we should mention this is first due to Riemann. And that's why I call, okay, so this is another way you can call this the Riemann zeta function, as opposed to the Euler product or the series, Dirichlet series, right? The thing has so many names. It's a Dirichlet series, has an Euler product. Yeah. The Riemann zeta, what's the line? The Riemann zeta function is a Dirichlet series studied by Euler, defined by Euler. Anyway, this is Gauss's conjecture. So Gauss said that when he was computing tables of primes and he was computing tables of logs, and he noticed that the density of primes around x was like 1 over log x. And so if that's the case, then you just take that density function dt over log t, and you integrate it from wherever 2, doesn't matter where you start, up to x. This is called the logarithmic integral function. And the error term, so this is asymptotic to x over log x, but x over log x is the wrong prime number theorem. The correct prime number theorem is this logarithmic integral function. This is called lie of x. And the error term, sorry? For Littlewood. Oh, for Littlewood. I never noticed that before. Okay. For Littlewood.
Is that true or are you?
I'm not actually sure.
Okay.
No. It's the logarithmic integral function. A lot. I don't know if this notation was used in Littlewood's time, and if it was, maybe it was introduced before Littlewood. Yeah, when was lie used for logarithmic integral? Maybe Gauss already used it. Gauss maybe knew that 100 years later there'd be a guy named Littlewood, first name Hardy. Okay, and the error term, right? So the error term, well, we would love to say something like, well, this we would really love. So this is the Riemann hypothesis. This is the Riemann hypothesis. And what does this mean? If I ask for the number of primes up to 1 million, or so say we want to know the number of primes up to, I don't know, 10 to the 100. Well, this will give us an answer, and the answer will be this answer is something like 10 to the 100 divided by 100. I'm just being very crude. 10 to the 100, that's x, divided by log x. Log x is about 100, just very, very crudely. I know it's a natural log and not a base 10 log. I guess it would be less crude if I put an e to the 100, but I don't know what e to the 100 is. I know what 10 to the 100 is. Okay, with an error on the Riemann, assuming the Riemann hypothesis, what's the error? So on RH, with an error of size 10 to the 50 square root. In other words, the last 50 digits are gobbledygook, but the first 50 are right. Okay, so we would know without counting, that's pretty bad.
Yeah.
Oh, that we know half of the digits accurately.
Yeah.
If we could get it more precisely, then there would be no zeros of the Riemann zeta function.
Okay, I like that.
And that would be, well, if they're to the left and they're to the right. Yeah. Yeah. So, yeah.
That settle the question.
Without counting any primes, the answer, first 50 digits of the answer, first 50 digits of the answer would be accurate. Do we know what percent? In other words, first half, i.e. first half. 1/2 of digits. First 50% of the digits are there. Do you guys know what percent of the digits we know today to be accurate? Nick is giving it away. What's that?
You're gonna be none of that.
It's going to be 0. Yes. Known today. 0% of the digits. So even getting 1% of the digits would require something like here having a 0.99 instead of a 0.50.
What is the error that we currently?
Okay, so so it's not hard to prove, not hard. And I did this last term or whatever. Not hard to show an error that looks like x times e to the minus a constant square root of log x. Now this is where analytic number theory gets its bad name from. What the hell is this thing? Right? You can't make sense of this until you realize what would it mean to get a 1%, if we had a 1% knowledge of the digits. Let's compare. This isn't the best known. We have a slightly, instead of log x to the 1/2, you can do log x to the 3/5 or something, but it's not anything. What's that? Okay, the 3/5. Great. So compare that to big O of x to the 1 times x to the minus 0.01, which is what that 99, if we knew 1% of the digits to accuracy. This, if I write this as e to the minus 0.1 log x, you can see the difference. So this is a thing that has a constant log x. This is a thing that's a constant log to the 1/2 or 3/5 x. So this is a much more slowly growing function, which means this is a much more slowly decaying function. But let's compare it to, for example, is this even greater than the order of magnitude here? What about 1 over log x? What is that? Compare to the main term, which is x over log x. So this is log x to the minus 1. And how can we write this as e? This is e to the log of this, which is minus log x. So the main term is less than x by a e to the minus log. Conjecturally, the error term, well, this is the main term. There's no big O. The main term has size x times this thing. Does that make sense? So the main term is indeed much bigger than the error term. And in fact, if you had any powers of log savings, they would still grow much more. So this is better than big O of x to the 1 over log x to the million. Because that would still just be some constant times log x. This is a constant root log x. Noticing that my battery is really low. Felt like I forgot something. Okay, now my computer won't die. All right. That was neither here nor there. That's I'm just telling you what some of the applications of why do we care about these zeta type functions. What's another application, not of maybe of zeta itself, other classical applications are to things like other than you guys, what else can you use zeta or more generally L functions for? Well, so this gives us very precise counting for primes. Convincing first years to become number theorists. Yes. They have to care about the number theoretic applications of this thing. But yeah, so for example, are there, here's the kind of thing that people were worried about in the 19th century. Are there, and long before, finitely many, well, first of all, are there finitely many primes? Right? Euclid settled that one. And of course, now we have very precise counts of just how quickly they grow. I mean, somewhat precise. What's that? That's right. That's right. I wonder what he would say about Euclid.
I mean, I think it might.
Yeah, anyway,
It's more properly expressed as for any finite.
That's right.
Primes, there's a prime not on the list.
that's right. That's right. That's exactly what Euclid proves. Yeah.
So I you probably deny that you can take the product of all of them or something, kind of wrapping back around.
Ah, the world is Z mod n for a large
Yeah.
unspecified n. Okay. There's merit to that. Okay. There are finitely many, not just primes, but there are there infinitely many, of course, infinitely many primes that we know. That's good. That's nonsense. Are there infinitely many primes that are congruent to 17 mod 23? Why you would ask such a thing, who knows? But this is the kind of thing you can ask. 1 mod 4. 1 mod 4 you can settle easily. 3 mod 4 you can settle by Euclid. 1 mod 4 you can settle by class. This is the kind of thing. Are there infinitely many primes in progressions? So you choose your favorite, 17. Oh God, I'm gonna have to add 17 and 23. That's not so bad. 30, 40. That's what I was worried about. And then the next one, I'm adding not 17, but 23. So that's 63. And oh, this isn't so bad actually. Okay, so anyway, whatever. This is a sequence of numbers. Is it going to be 80?
I don't know how it looks like.
I'm adding not 17. I'm adding 23. This is
It's the only prime on the list.
yeah. It doesn't look promising that we're going to find more primes. Is this sequence going to have more primes? And so special cases were known. Special cases of primes congruent to A mod Q. Of course, A and Q had better be coprime, or else there aren't many primes that are 5 mod 10. There's one, yes. So special cases were known before the general theory developed by Dirichlet. This is 1837. What he showed, actually following Euler, which is the first thing that Euler did with the Euler product formula, is something like if you take the sum over all primes in progressions, in a progression A mod Q with A equal prime to Q, of the reciprocal of the primes, that sum diverges. So not only are there infinitely many, there's so many that there are some of their reciprocals. So if I take 1/17 plus, I don't know what the next time I'm going to hit one is going to be, but whenever I do, if I take that series will diverge. Okay, so this was 109. Is that the next thing? 109, yeah, thanks. And then 2032. 132 is definitely not. Yeah, so the evens we can throw out, but is 109 prime?
It looks prime.
Feels prime. It is prime. Tastes prime. It smells prime. All right. It's not 57. Yeah. Is it 7 times 13? Yeah. It's not obvious.
Maybe it's not obvious to you.
Because it's got a 7 in it, right? The 2s, 3s, and 5s are easy.
And the squares.
And the squares, right? Right.
You go ahead and prize all.
Finally, after.
Look, if you show your 13 times tables, I don't know what.
A lot of times tables go up to 12.
I did not.
Okay, so what was it that he introduced to do this? The whole point of this little historical aside is that what did he the key objects that he discovered. I'm going to say discovered in this case. There's no way these things are not going to be known by aliens that come to visit us in their balloons that they send over. The key objects that he discovered are called Dirichlet characters. So let's discuss what Dirichlet characters are. I keep going back and forth, oscillating between whether I want to do this historically and here's what the objects were and how they were invented, or let's discover them ourselves. How would you figure this out? But what I really want is to understand GL1A mod GL1Q, this thing that I was alluding to. And in order to do that, we need to know what Dirichlet characters are. Or actually, we don't need to, but we'll discover by another method what Dirichlet characters are. But I think I want you to know classically what they are before we discover them in another way, so that you start recognizing them when they come up. Okay, so that was that explains this whole historical aside, hopefully, or something. Dirichlet characters. So a Dirichlet character is something very simple when you unpack it. It's just what is if you look at Z mod n Z, the multiplicative group of Z mod n. Okay, so these are numbers that are co-prime. This is the set of A mod n, so that A and n are co-prime. Okay, the residue classes mod n that are co-prime to n will be invertible. The whole right this is equivalent to the set of A mod n, such that there exists a B with A times B congruent to 1 mod n. This again is a Chinese remainder theorem. Okay, so we want to understand this is a finite. This is a locally compact, in fact, compact, finite abelian group. So we mumbled something about the character theory or the Fourier analysis on these things. We want to understand the characters. Now this is a multiplicative group. So let's understand the multiplicative characters. Multiplicative characters, functions chi from Z mod n cross to C cross. What can these things look like? Okay, so how many of you have seen Dirichlet characters before? Just out of curiosity, before I bore all of you. Okay, not all of you have seen it. Very good. So let's do this nice and. I'm not assuming that you've seen them. So let's do it nice and carefully. Give me an n. 17 is good. It's a little too special because 16 is a power of 2. You won't see. There's some features that how about let's start with 5. We'll work our way up to 17. So give me an n, 5, says I. N equals 5. Okay, so that's a nice prime. So we can work everything. What is Z mod 5 cross? What numbers mod 5 are invertible?
1.
6, yes. 1, 2, 3, 4. They're all invertible. 5's a prime. So it makes this field. Z mod 5 is a finite field. Okay, so, but what's the group structure? What's the structure of, in fact, Z mod P cross? Do you guys know this? That is correct. Why is that the case? So it's not true in general. Z mod n Z cross does not have the structure of Z mod n minus 1. Oh, because it's a finite field. That's true. That's true.
The polynomial, and then you look at its roots, and there has to be something of the appropriate.
Yes.
for it.
So this is a theorem of Gauss. This is Gauss's primitive root theorem. Gauss primitive root theorem. That every prime has a primitive root. So the group. So this is a cyclic group. The group Z mod P has a generator. So Z mod P cross always has a generator. Always has a generator. So this group is equal to just multiplication of a single element A. Is 2 a generator for infinitely many primes? Is 2 a generator for P infinitely often? Open problem. Just a little aside. On RH, okay, so let me not, that's a real aside. Let's get back to Dirichlet characters. So what is, in this case, who's the generator? Is 4 going to generate the group force? 4 is -1. -1 doesn't have a lot of things it can multiply to. Let's try 2. So if we try A equals 2, then A squared is 2 squared is 4. A cubed, we're working mod 5. That's right. And A to the 4th. In fact, so remember, A to the P minus 1 is always 1 mod P as long as A and P are co-prime. This is Fermat's little theorem. yeah, F little l. Okay, so so now that we know the group structure, we can work out what the characters are, because once you know the character on a generator, it forces by the fact that it's a homomorphism, it forces the values everywhere else. So we know that 2 to the 4th is congruent to 1. So whatever chi of 2 is, chi of 2 to the 4th is going to be chi of 1. The character at 1 has to be, it has to take the identity to the identity. And it's a multiplicative character, so chi of 2 to the 4th is chi of 2 to the 4th. So whatever chi of 2 is, it's a 4th root of unity. So our options are, so here are the elements A. The elements A are 1, 2, 3, and 4. The characters chi can give to any of the 4th roots of unity. So it can give to 1 or -1 or I or -I. Those are the possible values of 2. Of course, those will all be distinct characters. Let's call them chi1, chi2, chi3, chi4. They're all going to give 1 to the identity. Yeah. Okay, and now let's fill out the rest of the table. It'd be good to see the multiplication law. So what do I put for 4? Well, 4 is the square of 2. So I just have to square these numbers. So chi1 of 4 is, well, chi1 is the trivial character, right? We can see that already. It's just going to give, if it gives 1 to 2, it gives 1 to everybody. Fine. How about -1 squared? Okay. How about I squared and -I squared? All right. And then I want a cubed, which is 3, because that'll tell me what's here. That's 4 times 2. 4 times 2 is 3. So the value character at 4 times the character at 2 will give me the character at 3. So that's -1. This is -I, and this is I. So now we've worked out all 4 characters. And so let Z mod 5, the multiplicative group, hat be the group of characters, multiplicative characters. In other words, we found that there are 4, chi1 through chi4. What's the group structure of that? Right, you can multiply characters and get another character. So we get a group law. We have an identity. We have an inverse because we can invert, like we can invert each of the elements of C, and that'll still have the same structure. So the inverse of chi3 is chi4. If I multiply chi3 by chi4, I hope you agree you get chi1. Chi1 is the identity element. What's the group structure? It's a group of order 4. We only have 2 options. Klein group, Z mod 2 cross Z mod 2, or cyclic group, Z mod 4, which is it? Am I going too fast or too slow? I know for you guys it's too slow.
I don't think. I mean, I don't think it's easy to speak.
It is Z4. It is Z4. It is Z4 because Z mod 5 cross is Z4. The group and its dual are going to be isomorphic. Okay. So what are the generators? Yeah. But what are the generators? Or what's a generator? I think chi3. Chi3 generates everybody. And it has the same law as the powers of 2. Okay. So that's for a prime. Let's just see what happens for a non-prime. You wanted 17. 17 is going to have too many to write down. How about
You also just said a non-prime.
non-prime and just 17? Yeah. How about 12? So if n is equal to 12, this is another good. If you know what happens mod a prime, and you know what happens mod 12. I think you can work out the general theory. Mod 12. Okay, who knows all the characters mod 12? Think you know all the characters like this, mod 12?
I know what the elements of Z mod 12 cross.
Okay, good. Let's start there. So who's invertible to who's co-prime to 12? 1 is always there. 2 no, 3 no, 4 no, 5, not 6, 7, not 8, not 9, not 10, 11, and we're at 12. Okay, so again we get Z mod 4.
I know you're just dual group.
It's just the dual group. It's Z mod 4. What's 5 squared? Bless you. 25 mod 12. 24 is a multiple of 12. Uh-oh, 5 squared is 1. Obviously, -1 squared. -1 squared is 1, which is 11. And 7 squared, 49, is a 1. So actually, the group is not Z mod 4. It's Z. This is Z mod 2. This is the Klein group. So let's see what happens for the characters. So it's not enough to know what happens at 5. Right? I have to know what happens, for example, at 5 and at 7. Now I can determine the rest of the character table. So let's work out the character table. Sorry? 7 is -5. That's true. But then I need to know where it sends -1. Because -1 could go to 1 so they all have order 2. So the values can only be plus or minus 1s. So we have our characters, chi and A. Whoops. Let me leave a little room. A goes 1, 5, 7, 11. And our characters will be chi 1, chi 2. Well, I don't know how many chi's. Let's see. I could determine 5 and 7. Once I determine 5 and 7, 11 is 5 times 7. 5 times 7 is 35, which is -1. 36 is a multiple of 12. So once I determine 5 and 7, then I know everybody else. So 5 and 7 could both be 1s. Their squares have to be 1. They could both be, well, one could be, let's do it in order. Too much. They could both be 1s. They could be 1 and -1, -1 and 1, or -1 and -1. So that's 4 characters. The product of 5 and 7 is 11. So that's that, that's that, that's that, and that's that. And of course, the value at 1 is always 1. What's this? What's the structure of this group? Line 4. Everybody squares to 1, and the product of 3 and 4 is 2. You see that? Product of 3 and 4 is 2. So this is again Klein 4. Of course, these things are no accident. Okay, something funny is going to happen mod 12 that we didn't see mod 5. One of these characters, well, 2 of the characters are in primitive. One of them is the trivial character. This is the trivial character. One of the characters is actually imprimitive. What does that mean? So if I have a n1 dividing n, then if I have a character mod n1, oh, I have to explain zeros in order to explain primitivity. We haven't done that yet. In this case, it's really direct. Okay, I'm not ready for imprimitivity. Never mind. Never mind yet. Which one's imprimitive? 3. Yeah, right. Okay, we'll come back to that. Pause that discussion for just a second. Here's the funny thing that we're going to do that's going to look kind of like summing over the integers in the theta function, but dilating. Funny thing to do. Funny thing to do. Extend chi, which is born as a function on z mod n, a character, a nice character. We're going to extend it to a function on all of z mod n. That's a general fact about abelian. So if you have locally compact abelian groups, there's a canonical isomorphism. We can discuss that. Yeah, it'll take us a little off course, but it's something that we start seeing the first instances of in this very, very simple, with your bare hands example. Okay, so here's a funny thing to do. We're going to extend chi to a function on, it's no longer a character. It's going to take values in all of C via chi of A if A is not coprime to N. Chi of A, we're just going to set to 0. We're sort of ruining the multiplicative structure by allowing this chi to be defined on the full quotient. just zeroing out on the elements of the group Z mod n that are not coprime to n. If you are coprime to n, you take the value that Kai already assigned. Okay. And now I can say the thing I was trying to say before. It is I love this. You know, I guess I still love it. But when you start doing things adelically, you no longer go through this rigmarole. So okay, we'll see that later. Primitivity definition. If n1 is a divisor of n, and chi1 is a character mod n1, we can define the induced character chi to be so if we have a character mod n1 and we have a divisor, so we know what the values z mod n1, so here's z mod n1, sort of 1 through n1 or 0 through n minus 1, and here's another one, and here's another one, but then n is a multiple of n1. So all I'm going to do is I'm going to put the values of chi1. I'm just going to repeat the values of chi1. So I'm going to repeat the values of chi1 as long as a is coprime to n, because remember the character mod n might have other prime factors other than the prime factors that were in n1. So it has to be 0 if a is not coprime to n. But if a is coprime to n, then I put the value of chi1 of a. Does that make sense? So if I have a character mod 12 and I want to make a character mod 60 out of it, so if n, example, n1 is equal to 12, n is equal to 60. So if I take one of my characters mod 12 and I want to make a character mod 60, what I'll do is, which one should we take? One of these or something. Well, what I'll do is, you see some of the values. So I look at the numbers mod 60 and I break them into chunks mod 12. 1, 2, 3, 4. Oh, I accidentally got it right. And on the first chunk mod 12, I'll put the values of the character. Let's take chi3. I'll put the values of this character. 1, a bunch of zeros. What was it? -1, 1. -1, 1, -1. But here, sorry, even before I get started, the value at 5 is supposed to be -1. The value at 5 is supposed to be -1. But 5 is not coprime to 60. So I just take that -1 and I want to get a color. No, go away. I want to get a color. And I zero out that value of -1 here. But at the next instance, that 5 is 12 plus 5, it's 17. There's no problem with putting a -1 at the next instance of, there's a 1, -1, 1, -1. 1, -1, 1, -1. Now, some of these might land on multiples of 5. And when they do, instead of the multiple of 5, I put a 0. That's the induced character. So if I have a character mod 12, I can make a character mod 60 by zeroing out, by taking what should be the character mod 12, but just zeroing it out at places where that would clash with the fact that it has to be 0 if it's coprime to n. Does that make sense? So that's an induced character, and then we say a character is primitive if it's not induced from some smaller definition, or better yet, I'll say such a character is imprimitive. Such a character is imprimitive if it's induced from a divisor, if it takes on these values from a divisor of n1. So does that make sense? Does that make sense? Primitivity versus imprimitivity. If we look mod 5, are any of these characters imprimitive? So we have to look at divisors of 5, and there are no divisors of 5 because it's prime. Right? So these are all primitive. Okay, the trivial character, by the way, is always imprimitive because it's really a character mod 1. So this is the trivial character. It's the character where you take just all ones and you induce it to a character mod 5 by setting it to be 0 on multiples of 5. So this is imprimitive. The trivial character is always imprimitive. Unless you're mod 1. But, here, one of the characters is also imprimitive. This character is periodic mod 6. 6 is a divisor of 12. This is periodic mod 6. And 6 is a divisor of 12. So this is really a character mod 6 that we've dressed up to a character mod 12. 6 has the same prime factors as 12, so there's no zeroing anything out. There's no new coprimality conditions. So this is imprimitive. Imprimitive. The others, one needs to check that the others are indeed primitive. So these two are primitive. It would not be so pleasant to check for large n. You need to know what the group structure is. Yeah, well, but it's an important definition. Okay. Yeah, so we know so it's a definition. Chi is primitive if there does not exist an n1 chi1 such that chi is induced from chi1.
I was sort of hoping we could find certain not in.
Well, it's like primes. A number is prime if there aren't two numbers that multiply into it, right? Prime and primitive, it's defined by. Yeah, so a character is primitive if whenever there's a character that agrees with it on all divisors, that character is itself. Right. If there does not exist, thank you. If there does not exist, yeah. Or if whenever there does exist, it's equal to chi itself. N1 is equal to A. Okay. Gosh, what can I do in 4 minutes? So we've learned something about Dirichlet characters. We can either talk about what's called the twisted Poisson summation formula, which is how classically you get access to the L functions. Okay, let me define an L function. So define, given that given chi on z mod n, initially on z mod n cross, but it's been lifted to a function on z mod n by zeroing it out. We can extend it again to chi on either the naturals or even better up to z, of course, by composing with the mod n map. Compose with mod n reduction. And once you do that, you have access to something called a twisted Poisson summation formula. Poisson summation, which is a sum over, if you have a nice Schwartz function, f in Schwartz of the reals now, you can take a sum over the integers f of n, chi of n. And what's on the other side is the subject of the twisted Poisson summation formula. So in order to make sense of, or one way of proving a twisted Poisson summation formula is to give one more extension, one last extension, I think. Yeah, I don't, well, and then we're going to extend it delicately. One more extension, which is to chi to be a real value function. And once chi is a real value function, then chi times f is just a regular function. We could take its Fourier transform and see what's on the other side. Okay, so that's what we're going to have to do, I guess, next time. I'm a little, as you can see, I'm a little conflicted about whether to present more of the classical theory as opposed to going straight to the Adelic viewpoint of these things. But I think it is useful to know the classical thing anyway. Any objections to continuing a little bit classically? Okay. So we'll do a little bit more classically next time and work our way up to, I guess I should define one more object. The key object here is the Dirichlet L function. Dirichlet L function, Lejeune Dirichlet. I don't know if the L is for Lejeune, which is a summation, not just 1 over n to the s like the Euler or the Riemann zeta function, but you just put the character over n to the s. So in the case of IE or EG rather, in the case of what was that character? Mod 5, chi mod 5 was 1, and then let me just grab one of these. I, then negative I, then negative 1. Okay, so I, then negative I, and then negative 1. That was the character. So then this L series, which sometimes is written L sub chi of S or L of S chi, depending on your notation. So this is 1 over 1 to the S plus I over 2 to the S minus I over 3 to the S minus 1 over 4 to the S and nothing at 5 to the S. And then 6 starts it all over again. 1 I, negative I, and so on. Right, so that's the series, and these functions have applications to primes and progressions. Although I'm not going to go so far as to give that application. That would take us way too far off field. But I do want to recognize these L functions, and they have Euler products, right? Let me say one last thing is that this also has an Euler product, and then we're done. 1 minus chi of p over p to the s inverse. For exactly the same reason, it's a completely multiplicative function. Chi is completely multiplicative. Chi of n times m is equal to chi of n times chi of m, which actually you have to check for a second, because we've done all these manipulations when we lifted it. So certainly this is true if n and m are both coprime to the modulus, the modulus capital N. And when they're not, okay, then either side, both sides are 0. So because it's completely multiplicative, for the same exact reason, you get this Euler product formula from a series to an Euler product. And so we're going to recognize these things also as Adelic Poisson summation and Mellin transform things. To come later. Mixture of classical and modern viewpoint science. Okay.